Hello, everyone. I'm Yuan Tao from the Department of Psychological and Cognitive Sciences at Tsinghua University. Today, I'm excited to introduce our work called GeoCGA, which stands for Geometry-Aware Cross-Modal Graph Alignment. This method is designed for referring segmentation in 3D Gaussian splatting. The main goal of our work is to accurately locate and segment the target object described by a natural language expression within a 3D Gaussian scene. We propose a geometry-aware cross-modal graph alignment framework that significantly enhances spatial reasoning capabilities, enabling more precise and reliable identification of objects based on language descriptions. Let's look at the problem and motivation behind referring 3D segmentation. The task is to take a 3D Gaussian scene and, given a natural language query, predict a relevant score for each Gaussian to segment the object being referred to. There are two fundamental limitations faced by current methods. First, language encoders like BERT don't have explicit positional priors. This means spatial terms like left or above are treated just like ordinary words, without truly capturing their geometric meaning. Second, the cross-modal attention mechanism tends to be self-reinforcing. If early alignment between language and 3D data is off, those errors compound and get worse during training. On the right, the figure illustrates this issue. In the top row, with simple descriptions, both refer splat and our method successfully locate the object. But when spatial cues are introduced in the bottom row, refer splat mistakenly segments the wrong area, while our approach, GeoCGA, still grounds the object correctly. This highlights the importance of addressing these spatial understanding challenges in referring 3D segmentation. Based on our empirical analysis of refer splat, we have identified three key insights. First, spatial reasoning cannot be achieved through language co-occurrence alone. It requires explicit geometric structure on both the linguistic and 3D sides. This means that understanding spatial relationships involves more than just the words used. The model needs a concrete geometric framework to interpret these relations accurately. Second, achieving robust grounding means we have to align relational structures at the graph level, rather than relying solely on node-wise feature similarity. For example, when referencing the chair to the left of the table, it's not enough to match the word chair. The spatial relationship of the table must be verified as well. Third, cross-view geometric supervision is essential for maintaining stable spatial correspondence when the viewpoint changes. This means that the model's response to the same 3D object should remain consistent, no matter the angle from which it's viewed. These three insights are fundamental and have directly shaped the design of our approach. Here we have an overview of the GeoCGA framework. The process begins with GAPE, or Geometry-Aware Prompt Expansion, where we use a large language model to parse the natural language query into entities and their spatial relationships, forming a semantic spatial graph. Next, in the 3D scene graph construction step, we extract object-level representations from the 3D scene using Dr. Splat, creating a geometric graph where nodes represent objects and edges encode distances and directions. Then comes CMGA, or cross-modal graph alignment, which matches structures at both the node and relational levels to ensure the spatial relationships described in a language align with the geometric relationships in the 3D scene. Finally, we apply geometric consistency supervision, enforcing consistency across multiple rendered views to stabilize grounding. The overall training loss combines this alignment loss with a geometric regularization term to optimize performance. On this slide, we're diving into the core of the GAPE and 3 DSGC modules, which work together to build two complementary graphs. Starting with GAPE, it uses a large language model to break down the input query into structured entities and spatial relations. For example, if the query mentions the object sitting on the stool near the apple, GAPE parses out the distinct entities like target object, stool, and apple, along with spatial qualifiers such as on and near. These enriched queries get re-encoded, producing geometry-aware embeddings that explicitly capture spatial context. From this, GAPE constructs a semantic spatial graph where nodes represent entities, and edges define their spatial relationships. On the other side, 3DSGC operates in the 3D domain, using the pre-trained Dr. Splat model to extract object-level features. Each node contains positional and color information, while edges encode distance and direction between objects. This graph is further refined through a message passing mechanism with learnable functions, enabling the embeddings to incorporate higher order spatial context beyond just pairwise relationships. Together, these two modules create structured graphs, one from the language perspective and one from the 3D geometric perspective, that can be directly aligned for deeper spatial understanding and reasoning. This dual graph approach is key to bridging textual queries and 3D scenes effectively. Here, we have two modules, CMGA and GCS. Starting with CMGA or Cross-Modal Graph Alignment, it works on two levels. At the node level, it calculates a softmax similarity matrix between textual entities and Gaussian representations of 3D objects, which helps align the text with the corresponding parts of the 3D scene. On the relation level, it ensures that spatial relationships described in language, like left of, are consistent with geometric edge attributes in the 3D space. These two alignment aspects are optimized together through a joint loss function. Moving on to GCS, or Geometric Consistency Supervision, the challenge here is that aligning from a single viewpoint can cause a model to drift when presented with novel views. To solve this, we penalize variations in Gaussian responses across different views using an L2 consistency loss. This encourages a model to learn a globally coherent 3D interpretation, not just viewpoint-dependent correlations. Finally, the total loss combines both the alignment loss from CMGA and the geometric consistency loss from GCS, with a balancing parameter lambda, controlling the strength of the geometric regularization. This integrated approach helps create a more robust and spatially consistent understanding of the 3D environment aligned with the linguistic input. Here we present our key experimental results across 3 benchmark datasets. Starting with the table on the left, RefLERF focuses on fine spatial reasoning with complex scene layouts and heavy occlusions. Our GeoCGA method achieves the best scores in all 4 scenarios, RAM, FIG, T, and KIT, with an average improvement in mean intersection over union, or MIOU, of 20.8%. Notably, the kitchen scene sees a remarkable 50.7% boost, reflecting GeoCGA's strength in handling intricate spatial relationships described in the queries. On the right, the LERF-OVS dataset evaluates open vocabulary segmentation. Here, we observe an average gain of 5.7%, with a significant 13.8% increase in the T-time scene, underscoring our method's ability to generalize across diverse object categories. At the bottom, you see summary figures, a 20.8% improvement on RefLERF, 5.7% on LERF-OVS, and a smaller 1% gain on the 3D OVS dataset. That smaller gain for 3D OVS is expected since the baseline performance is already very high, above 93%, leaving less room for improvement. Overall, these results clearly demonstrate the effectiveness of GeoCGA in advancing spatial and open vocabulary segmentation tasks. Here we focus on the ablation study and computational efficiency of our model. Starting with the left table, we examine the contribution of our core modules. The baseline model without any graph structure sets our reference point, showing performance scores of 28.3 and 20.1 in the SEM and Geo columns respectively. When we add just a semantic graph, there's a noticeable improvement, an increase of 1.2 and 2.7 points. Adding only the geometric graph yields even larger gains, improving by 2.1 and 6.4. However, the most significant boost comes when both semantic and geometric graphs are combined, achieving improvements of 3.8 and 10.2 points, which clearly demonstrates that these two graph structures work complementarily to enhance performance. On the right side, we assess computational efficiency compared to the reverse-splat method. Our approach reduces the number of parameters by about 57.8%, from 304 million down to approximately 128 million. Similarly, the floating point operations per second, or flops, decreased by around 39.6%, from 41.8 billion to 25.3 billion. This efficiency gain largely results from performing inference at the object level rather than the Gaussian level, alongside using a lightweight graph convolutional network module. Finally, key insights highlight that edge-aware message passing outperforms a standard graph neural network by 0.6 and 1.2 points. The geometric consistency loss is more effective than the pseudo-mask loss, improving results by 1.2 and 0.9. Additionally, explicitly matching relationships between objects leads to better outcomes than implicit methods. Each of these design decisions contributes positively to the overall model performance and efficiency. Let's take a look at the qualitative results. On the left side, we have Figure 1 showing comparison between ReferSplat, our GeoCGA, and the ground truth across different scenes and queries. The top row shows ReferSplat, which often struggles with accurate localization or produces coarse masks. In contrast, our GeoCGA results, shown in the middle row, closely match the ground truth at the bottom, demonstrating more precise and consistent segmentation. On the right, we visualize the learned relation graph refinement. The initial k-nearest neighbor graph contains many noisy edges. After training, the model effectively suppresses spurious relations. For example, the edge between chopsticks and a cup drops from a weight of 1.0 to 0.48. At the same time, it recovers meaningful connections, like the edge between a croissant and eggs increasing from 0 to 0.66. Of course, there are some failure cases too. When the scene contains multiple visually similar objects and the reference is ambiguous, the model sometimes only achieves partial segmentation. This highlights areas for future improvement. To wrap up, our work has three main contributions. First, we introduced geometry-aware perspective embedding, which explicitly integrates spatial structure into linguistic features. Second, we developed a cross-modal graph alignment framework that enables joint reasoning over both linguistic and geometric graphs. Third, our approach achieves state-of-the-art results on three key benchmarks, RefLERF, LERVS, and 3DOVS, with significantly fewer parameters, reducing model size by 57.8%. Looking ahead, we plan to focus on end-to-end differentiable object discovery to reduce dependence on pre-trained models. We also aim to design scalable graph matching algorithms capable of handling large-scale scenes and extend our framework to support open vocabulary 4D reasoning. Thank you all for listening, and I welcome any questions you may have.